As I said in the last video, there is a nice interpretation of the projective plane. I'll try to demonstrate it with this knife that I have and this onion. I really want to do this with an orange, but we're out of oranges, so this onion has to do it. Let me remove this. Okay. So first thing, let's just look at this knife. You can think of this knife as representing a three-dimensional plane, right? So it's let's say it's a cut that I just move a linear motion and I cut along a plane. If you notice that if I cut along a plane, when my cut meets this piece of paper, it leaves its mark as a straight line. So if I cut the space using any plane, I will get its mark as a straight line on this piece of paper. This is again follows from the geometry of planes in three-dimensional space, right? Because two planes in the three-dimensional space intersect at a line, at a straight line. Okay, what does that have to do with this onion? Well, on this onion, cuts that go through its center leave a particular type of mark around its boundary. Actually, I'm not going to cut this onion yet because I actually need it. But imagine that I'm cutting this onion with this knife, and my cut goes through the center of this onion. Okay, so just to imagine I'm cutting it like this. What would be the result? The result would be a circle on this onion that goes, wraps all around, right? So it goes, let's say, all the way like this, and so on. This is known as a great circle. A great circle is a circle on the boundary of the onion that is created by a cut that goes through its center. What do we know about great circles? Well, great circles have very nice and symmetric properties. In particular, every two great circles intersect twice, right? So this is the black great circle. And then if I draw another great circle, let's say I put this onion like this and I cut it like this, then I would get, for example, this red great circle. It will create this intersection point with a black great circle and then wrap around, and I will have another intersection over here. Did I mess up? Yes, I messed up my... Okay. Alright, so I have this red great circle that goes around like this, and I have this black great circle that goes around like this, and they intersect twice. Once here and once over here in the back. What does this have to do with projective plane? There is a nice interpretation of lines and points using this ball. So let's say I leave this ball like this. Okay, so that's the North Pole, that's the South Pole, and then these are just great circles on them. Based on what I thought, but I told, any great circle can be represented by a cut that goes through the center. Also, the same cut also leaves its mark on the piece of paper via a line. So this red great circle that I have on this onion will create, for example, I'm cutting like this. So let's say it creates, I'm cutting like this, it creates this red line. Okay. So if my onion is like, my onion is like this, then my red great circle creates that red line over there. But you could look at the red line as the shadow of this great circle. I mean, this is obvious, right? Because if I think of the red line as the shape of this, as the mark of this cut, then it's also the shadow of this red circle made via a point of light that is at the place at the center of the onion. So imagine a point of light at the center of this onion, and that, let's say, it emits light. Then the light that the shadow that this great circle creates will be at the exact same spot of when my knife touches the plane. Okay, so therefore the shadows of great circles are lines on the plane. What are the shadows of the intersection points? As I said earlier, The intersection points, so for example, if I hold my ball like this, two great circles intersect twice. One intersect over here, but this one doesn't make a shadow because the shadow will be going upwards, right? It will not create a shadow on this piece of paper. But the point that is at the back will create a shadow, will be at the position of the intersection point of this red and the black lines. Okay, and that's obvious. So now let's look at the geometric plane. I claim that the shadows of the great circles are basically lines in the projective plane. What about the line at infinity? Well, interestingly, the line at infinity has a very interesting interpretation. The line at infinity is the equator of this ball, because the equator is the only circle on this ball that does not create a shadow. Because when you look at the equator is created by a line, by a cut that goes parallel to this piece of paper. Okay, this parallel line will not, or this parallel cut will not actually intersect this piece of paper in this sense, and its mark will be the equator. So therefore I could say that the interpretation of the equator is a line at infinity. And with this interpretation, every great circle will create a line. If my cut is not parallel to the piece of paper, I will always get intersection with the paper, so therefore it will always leave a shadow, or the great circle that corresponds to that cut will leave a shadow. The only cut that does not leave a shadow is the cut that is parallel, but that leaves me with the equator, which is the interpretation of the line at infinity. What about parallel lines? Well, parallel lines also have a very interesting interpretation. Parallel lines are lines that intersect at point at infinity. So if I pick up this this onion and I pick a point on the equator, so let's say this point, and I create cuts that go through that point on the equator, so let's say this cut and this cut. Okay. Then the shadow of those two cuts will be, I don't know how to represent this, show this, but the shadow of the cut that goes like this and a cut that goes like this will be two parallel lines on the plane. And of course this is based logically, this is what we expect, even though I guess seeing it is a bit difficult in this video, but basically these two cuts will be two lines, but they do not intersect anywhere in the ordinary sense, because their intersection is at the equator, which will not create a shadow. So when I look at the shadow of these two cuts, you will not actually see any intersection in the shadow of two cuts on the plane, so therefore they must be parallel. Okay, so parallel lines are simply lines that intersect on the equator. This interpretation, or this view of projective plane has a very nice feel to it, because now I could see how lines are actually circles. Remember that in the previous video we saw a bunch of weird properties of projective plane, that how lines were circles. Well, we can actually see that this circular shape here. Another nice thing that we can observe about this is that there is really nothing special about parallel lines. Think of, again, the lines as shadows of great circles. If I rotate this great circle, like this, then these two parallel lines, they are no longer parallel. I mean, I'm not changing anything fundamentally about the geometry or the structure of the line that I drew on this ball. But the only thing I'm doing is just rotating it around. But now if I look at the cuts that are made like this and like this, those two cuts will leave actually a mark, will have an intersection on the piece of paper. So therefore, there is really nothing special about parallel lines. If you interpret the parallel lines as great circles on the ball, you can just rotate the ball a little bit, and then those lines won't be parallel anymore. How does this help us? This helps us to get rid of a whole bunch of exceptional cases. You'll know that in the normal geometric plane, when I have a bunch of lines and points and stuff like that, I sometimes need to consider special cases of what if the line 1 is parallel to line 2, and etc. The interpretation of the projective plane tells me that I don't need to consider any such exception, because parallel lines are just like normal lines. They just intersect at the equator. Therefore, if I don't want to deal with parallel lines, I could just pick my ball, rotate it randomly, and then it's very unlikely that any of the great circles that I drew will be at the equator. So then therefore I will have normal intersections. There is one more interesting consequence, and that is the following. To understand the structure of a two-dimensional projective plane, we had to go to 3D to look at the structure of a ball, of circles and a ball. But we can do the same thing with the 3D. In 3D, when I look at a plane, I could think of a plane as having a line at infinity that surrounds it. Because in the normal 3D space, if you take any two planes, they intersect at a line, right? So that's what we started with. If I pick this plane that is represented by my cut through the space and this piece of paper, they leave a line. The only two planes, or only planes that are parallel to each other, that don't have intersection. But I could fix that by assuming that two parallel planes intersect at a line at infinity. To fully represent this projective space, projective two-dimensional space, I need to go to 4 dimensions and understand the structure of great circles around a 4-dimensional ball. I obviously cannot imagine a 4-dimensional ball, but I can understand the structure of a 4-dimensional ball by looking at the properties of the 3-dimensional projective space. The same way if you had a bunch of creatures living on this 2-dimensional space, they might not understand the 3-dimensional space, but if they understand the structure of projective plane, then they know how it feels to live on the surface of a 3-dimensional ball. The same way, if you can understand the geometry of 3-dimensional projective space, then we can understand how it feels to live on the surface of a 4-dimensional ball, and so on. So I think this is a very nice interpretation, and later on during the course we're going to use some of this intuition that comes from projective plane to simplify our understanding of geometric algorithms.